In the jogging tracks analogy, the tracks represent orbitals. I called them, in the analogy, S tracks, P tracks, and D tracks. Well, in reality, we have what are called S orbitals, P orbitals, and D orbitals. And an orbital is a three-dimensional region of space where an electron may be found. Just like a jogging track was a region where you might find a jogging electron. In a generic electron configuration, for example, 1s2, 2s2, 2p6, 3s2, 3p6, and so on, the coefficient represents the number of the energy level, and the coefficient is the number in front of the S or the P or the D. So I've shown here with these arrows, and I think they're going to wiggle here. Look at that. Those are the coefficients. That represents the number of the energy level that the electrons are in. So you can see here that there are only 2 electrons in the first energy level. In the second energy level, there are a total of 8 electrons in the second energy level. 2 of them are in the 2s orbital, 6 of them are in the 2p orbitals, but in the second energy level there are a total of 8. And here, what is shown, there are 8 electrons right now in the third energy level. The superscript, which is written up and to the right, indicates the number of electrons in those orbitals. Those are the superscripts right there. In general, as the energy level number increases, electrons have more energy and they're farther from the nucleus. So this is kind of similar to the jogging tracks analogy. We said that the easier tracks fill up first, and the easier tracks were smaller. Kernel electrons are in the inner energy levels. They're close to the nucleus. They're sometimes called core electrons. Valence electrons are in the outermost energy level. And of course, in any atom, there's only one outer energy level. There could be several core levels, but there's only one valence energy level. These valence electrons are muy importante, as the Germans would say. Well, the Germans who speak Spanish would say that. Anyway, the valence electrons are very important because those are the ones that are involved in chemical bonding. The kernel electrons, whatever. We're not nearly as concerned with the kernel electrons as we are with the valence electrons. So, if we write some electron configurations, we can see that helium has 2 valence electrons. It only has a first energy level, so that must be the outer energy level, and there are 2 electrons there. If we write the shorthand electron configuration for neon, we covered shorthand electron configurations in a previous lesson, so if you're a little rusty on that, feel free to go back and figure out what we mean by a shorthand electron configuration. We can see that neon has a total of 8 valence electrons, and the valence shell for neon is the second energy level. For argon, we also have 8 valence electrons. What about for krypton? Here's the shorthand electron configuration for krypton. We write R, and then 4s2, 3d10, 4p6, and we say, well, how many valence electrons is that? And some students want to add up all of these superscripts and say 18. But recall that the coefficient, in other words, this 4 here, this 3 here, and this 4, the coefficient represents the number of the energy level. And so the outer energy level is the 4th one. In other words, these d electrons are not valence electrons. And in general, you never consider d electrons to be valence electrons. The most valence electrons you can have is 8. Now, These are all noble gas atoms. They have full valence shells. They are stable, low energy, and unreactive. Having a full valence shell is a really low energy state for an atom, and that's going to lead into what we talk about next. Other atoms want to be like noble gas atoms. Of course, atoms don't really want anything. They just seek low energy states. But if we personify, to do that, to try to become like a noble gas atom, they give away or they acquire electrons. Now, an atom can't become a noble gas atom because it doesn't have the right number of protons, and the number of protons in regular chemistry, can't touch this. But other atoms can try to become similar to noble gases by either giving away or acquiring electrons. And the octet rule is the tendency for atoms to want 8 electrons in the valence shell. So let's look at a fluorine atom. And fluorine on the periodic table is right there. You can see that it is 1 electron shy of becoming like this noble gas, which is neon. So what could it do to become like a noble gas? Well, it could acquire 1 electron. If it does, it'll still have 9 protons because the protons won't change, but it'll have 10 electrons, which is like a noble gas has. In that case, it has a net charge of 1 minus, because of course the electrons are negatively charged, protons are positively charged, and so in reality a fluorine atom would actually rather be a fluoride ion. It would rather have 10 electrons than the 9 that it started with. Let's take another atom. How about chlorine? Chlorine is right below fluorine. It has 17 protons and 17 electrons. How could it become like a noble gas? Well, it would do the same thing. It would acquire or steal somehow 1 electron so that it would have 18, which is the same number of electrons that this noble gas has right next to it, argon. If it does acquire 1 electron, it will have the formula Cl-. So, just like fluorine, chlorine would actually rather gain 1 electron, and it would rather be a chloride ion than a chlorine atom, just like a fluorine atom would actually rather be a fluoride ion. You might guess, if we did this same sort of analysis for bromine, which is right underneath chlorine, how many electrons it would want to gain. And if we did this same analysis for iodine, which is right underneath bromine, I'm circling it here in the upper right corner with my laser pointer, you can guess that that would want to gain 1 electron as well. In other words, all of these atoms in this column, in this group, want to gain 1 electron. Let's go to the other side of the periodic table. How about lithium? Lithium's right there. How could it become like a noble gas? Well, it would give away 1 electron, because if it gives away 1 electron, it's going to have 2 electrons, like helium. The whole point here is to become like a noble gas. If it loses an electron, or gives 1 away, it will have a net charge of 1 plus. So in reality, a lithium atom would frankly rather be a lithium ion, because in doing so it would have a full outer shell, which is a low energy state. How about sodium? Sodium has 11 protons and 11 electrons. It would prefer to give away 1 electron so that it can have the same number of electrons as this noble gas, which is neon. Sodium atoms would rather be sodium ions. So you can see that we've looked at a few atoms and we've decided what they would want to do such that they could become like a noble gas. So here are the charges that certain groups of the periodic table take. Group 18, which is the noble gases, the groups are numbered from the left. This first column is group 1, the second column is group 2, group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, good. I wanted to make sure I put the right number of groups in there. 18. We talked about fluorine and chlorine. They are group 17. All of those atoms tend to gain 1 electron and get a -1 charge. Well, what about the group next to them? Wouldn't they want to gain 2 electrons? And that would be yes. And how about the group next to them? Wouldn't they want to gain 3? And if you gain 3 electrons, you gain 3 negative charges, so you have a charge of -3. Let's go back to the other side of the table. We talked about lithium and sodium, that they want to lose 1 electron, and therefore would get a +1 charge. Well, what about the group 2 elements? If the group 1 elements want to lose 1 electron, wouldn't the group 2 elements want to lose 2 and get a net 2+ charge? We're going to skip the D block because they aren't considered to be valence electrons, and we'll go to this group, which is group number 13. All of those guys would want to lose 3 electrons.